Hi, let me test my slides.
Sure.
Okay, are you seeing?
Yeah, and yeah, I just saw it just went to the second slide
Great.
as well. So
Thank
all is
you.
well. Yeah, we can. So Vishwas, do you want to go to a presentation mode or something, or this is fine? Yeah, okay, cool. For the other speakers in the session, Dean, do you want to just try out and make sure that the share works and so on?
Looks good.
Yeah, all's well. I still don't see Liang yet. So we'll start in about 4 minutes. Yeah. Okay, maybe let's get started. Welcome everyone to the last session of Random 2021. So we have a series of talks on de-randomization, pseudo-randomness, and friends. So the talks will be for 8 minutes with a little bit of buffer time to set up between talks, but there's going to be a discussion. There's going to be time for discussions right after this session. So in case there are questions that spill over something, we could discuss them in the session. And if you have any questions, please add them in the chat and we'll relay it to the speaker at the end. So our first speaker, first speaker will be Bhargav Thanke, who will be talking about hitting sets for orbits of circuit classes. Bhargav, do you want to set up?
So is my screen visible?
Yeah, the screen is visible. Do you want to go
Okay.
into the slideshow mode
Yeah.
or something?
So this is the slideshow mode.
So somehow we still see your whatever the
Okay,
PowerPoint
okay.
screen.
Okay. Yeah, let me do that. Okay, now do you see the slideshow mode?
Yes, now,
Okay.
now it's fine.
Yeah. So hi, I'm Bhargav and I'll be talking about our work hitting sets for orbits of circuit classes and polynomial families. So let me begin by introducing the polynomial identity testing or the PIT problem. So in PIT, we are given black box access to an arithmetic circuit F, and we want to check if F computes a zero polynomial or not. An arithmetic circuit is an algebraic analog of a Boolean circuit and is a natural model to compute polynomials. Now, because of the De Mello-Lipton-Schwarzschild lemma, we know that PIT is in co-RP. However, to date, no efficient deterministic algorithm is known, even when circuit is given. Now, PIT has interesting connections to many problems in algorithm designs and proving lower bounds for arithmetic circuits. For example, it is known that PIT is essentially equivalent to proving lower bounds for arithmetic circuit. And it turns out that PIT is to be a hitting set for a circuit class C if for all non-zero polynomials f in C, there exists a point A in H such that f of A is non-zero. Since this work focuses on hitting sets for orbits, let me define what orbits are. So for an n-varied polynomial f, the orbit of f is the set f of ax plus b, where A is an n cross n invertible matrix and b is a vector in f to the n. And for a circuit class C, the orbit of C is the union of orbit of f for all polynomials f in C. In this work, we give efficient hitting sets for orbits of certain well-studied circuit classes and polynomial families. Now, before I tell you about our results, let me quickly motivate the problem of studying hitting sets for orbits. So one of the motivations comes from the power of orbit closures. The orbit closure of a circuit class C is a set of all polynomials that are well approximated by polynomials in the orbit of C over the field of complex numbers, and orbit closures of simple and seemingly weak circuit classes can be quite powerful. Let me illustrate this statement by some examples. The first example is that of the sum product polynomial defined as follows. The orbit closure of the sum product polynomial captures depth 3 circuits, and because of the work of Gupta, Kamath, Kayal, and Saptarshi, we know that depth 3 circuits are quite powerful. In fact, we know that polynomial time hitting sets for depth 3 circuits imply sub-exponential time hitting sets for general circuits. The second example is of read-once formulas. So an arithmetic formula is just a special type of an arithmetic circuit, and a formula is said to be read once if every variable labels at most one of the leaves in the formula. Now, it is known that the orbit closure of read once formulas capture general arithmetic formulas. The third example is that of the iterated matrix multiplication, or the IMM polynomial. The IMM W, D polynomial is the 1,1th entry of the product of D many W cross W matrices whose entries are distinct variables. It is known that every polynomial computed by a size S formula is in the orbit closure of IMM3, poly S, and every polynomial computed by a size S algebraic branching program, or ABP, is in the orbit closure of IMM S, S. So to summarize, hitting sets for orbit closures of simple models imply hitting sets for general models like formulas, ABPs, and circuits. So as a first step towards designing hitting sets for general models, it makes sense and it is natural to try to obtain hitting sets for orbits. Now, there are other motivations to study hitting sets for orbits of circuit classes as well, and I talk about those in the full version of the talk. So now let me move on to our results. Since our first result is about hitting sets for orbits of read-once oblivious algebraic branching programs, or RABPs, let me define what these are. So with W with matrices to Mn and the all-ones column vector, the matrices M1 to Mn are W cross W matrices, and their entries are univariate polynomials in the variables x1 to xn respectively. ROBP is said to be commutative if the matrices M1 to Mn commute. So our first result is a ND to the order D log W time hitting set for the orbits of commutative RABPs with individual degree at most D. And this result as a corollary gives quasi-polynomial time hitting sets for the orbit of the sum of product of low degree univariates, the elementary symmetric polynomials, and low individual degree sparse polynomials. Prior to this work, a quasi-polynomial time hitting set was known for RABPs because of the work of Agrawal, Gurjar, Kurwar, and Saxena. And in a simultaneous and independent work, Bedini and Shpilka gave a quasi-polynomial time hitting set for orbits of sparse polynomials, while in a subsequent work, Bhargava and Ghosh gave an improved quasi-polynomial time hitting set for this model of commutative RABPs. Our second result is an n to the order W to the 6 log n time hitting set for orbit of multilinear with W RABPs, and as a corollary, this gives quasi-polynomial time hitting sets for orbits of IMM3, D. In a simultaneous and independent work, Medini and Shpilka gave a polynomial time Hitting set for the orbit of the continuum polynomial, a polynomial which can be computed by multilinear with 2 RBPs. And in the subsequent work, Bhargav and Ghosh gave improved quasi-polynomial time Hitting sets for the model of constant with RBPs. Our third and fourth results are about occur-K formulas. So let me define what these are. An arithmetic formula is said to be occur once if its leaves are labeled by sparse polynomials and every variable appears in at most k of these leaves. Also, instead of just the usual sum and product gates, an occur-K formula can also have power gates. So an occur-K formula is a natural generalization of a read-K formula, and it captures several interesting circuit classes like depth 4 multilinear formulas with constant top Fanon, a model that has been studied intensely in the literature, and polynomials like the power symmetric and the sum product polynomials. Our third result is a ND to the order log s time Hitting set for degree d polynomials in the orbits of constant depth, constant occur formulas. This improves to a ND to the order b time Hitting set if the leaves are labeled by b-weighted sparse polynomials. And as a corollary, we get quasi-polynomial time Hitting sets for orbits of multilinear depth 4 formulas with constant top Fanon, and polynomial time Hitting sets for orbits of the power symmetric and the sum product polynomials. Prior to our work, a polynomial time Hitting set was known for constant depth, constant occur formulas because of the work of Agrawal, Saha, Saptarshi, and Saxena. And polytime Hitting sets were known for the orbit of the power symmetric polynomial because of the work of Koiran and Skomra. Our fourth and the final result is a ND to the order log n plus log s time Hitting set for degree d polynomials. The orbits of size s occur once formulas, and this improves to a ND to the order log n plus b time Hitting set. The leaves are labeled by b-weighted polynomials. In a simultaneous and independent work, Medini and Shpilka gave a quasi-polynomial time Hitting set for orbits of read once formulas. Some of the techniques that go into proving these results are rank concentration by translation, algebraic independent space techniques, and the Shpilka-Volkovich generator. I don't have time to talk about those in this talk, but I do talk about those in the full version of the talk. So now let me conclude by mentioning some open problems. The first problem is designing efficient Hitting sets for orbits of the IMM in the determinant polynomials. Now, as we saw the orbit closures of these polynomials are quite powerful, so it is natural to try to obtain Hitting sets for orbits of these polynomials. The second problem is to remove the low individual degree restriction from result 1, a result on Hitting sets for orbits of commutative RBPs. The third problem is to prove lower bounds against orbits of RBPs, and the last problem is to design efficient Hitting sets for orbits of RBPs. So that's about it. Thank you.
Thank you. Are there any questions? We have a little bit of time for questions. You could maybe ask in chat, and maybe I'll ask a question. So, so is Hitting sets for orbit, does your thing also extend for orbit closures of these classes, or is it only for orbits?
Oh, it's just for the orbits.
Okay. And I guess in the definition of orbits also, the matrices involved were invertible. And is that also crucial?
Matrices are arbitrary. You get affine projections, and even affine projections of things like Riedeman's formulas are quite powerful. So yeah, the distinction of matrices being invertible is crucial.
Okay, and is there a connection between the two? Like, for instance, if you could handle affine projections, would that say something about the closures or the other way around?
So affine projections are contained in orbit closures. Right, but so if you are able to do Hitting sets for affine projections of some models, like say sum product polynomials, then you would be able to come up with Hitting sets for depth 3 circuits. So even just handling affine projections would be quite good.
Okay.
Right. So like sort of orbit closures are like a generalization of affine projections.
Okay. Okay. Are there any other questions? Okay. If not, let's Bhargav. And the next talk will be by Vishwas Bhargava, which, I mean, the result was mentioned multiple times in Bhargav Tanke's talk. This is on improved Hitting sets for orbits of ROABPs. We can see the slides, but we can't hear you.
Hello?
Yes, we can hear you now.
Oh, wow. Okay. Never mind. Uh, Hi. So I hope everyone can hear me and see my slide. So I'll also be talking about hitting sets for orbits of circuit classes, in particular ROABP. A lot of my talk would be overlapping with Bhargav's talk, so I'm sorry for that. Uh, so I'll also be talking about PIT problems. So PIT, you are given an arithmetic circuit and with some size, and you want to check if it computes an identically zero polynomial. So there are randomized solutions for this by just evaluating it at random points. But we want to look at the randomization of this problem, which is one of the most de-randomization problems out there and has lots of applications in various fields. So the focus of this talk will be on black box PIT, where you can't see the circuit, as opposed to white box PIT, where you can see the internal working. So the notion of black box PIT and hitting sets are equivalent. So let me focus on what a hitting set means. So for a circuit class, a hitting set is a collection of points where you are promised that for each polynomial in the circuit class, there is a non-root in your set. As I mentioned before, these are equivalent notions. So I'll be talking about hitting sets. So the protagonist of this talk, as well as the previous one, was orbits of polynomials. So orbits of polynomials, you take a polynomial and you look at the collection of polynomials that you get by applying various invertible linear transformations. So similarly, for orbit of a class of polynomials, it's just union of orbits of each and every polynomial in the class. So looking at orbits gives very interesting ways of looking at new classes uh, from older ones. So let me give few pointers about importance of studying orbits. So first one, I think it's just to the natural question of checking the sturdiness of the approach and the techniques you already know and see if they can be applied to orbits in some way. The second is that orbits of simple polynomials have very great expressive power. So as mentioned by Saha Thanke, so this observation says that if you look at affine projections, that is, if you look at matrices applied to a polynomial with which they are not necessarily invertible, they are contained in the orbit closure of a family. So this simple observations have lots of interesting implications. It says that orbit closure of read once formula, very simple class, contains all formulas. Orbit closures of ROABP, something we know a lot about, contains ABPs, and also you can say things for very specific classes as well, not just the whole formulas of ABP. Like the depth-3 circuit is contained in orbit closure of one simple sparse polynomial. And also that constructing hitting set for orbits of polynomial class makes it independent to a choice of coordinate system, which makes it mathematically and geometrically more robust. So all the work on hitting sets for orbits has been just done this year in a span of few months. So first was by Medini Spilka, who gave quasi-polynomial hitting sets for orbits of sparse polynomials and read-once formulas, followed by work of Saha Thamke, who gave hitting sets for orbits of ROABP and constant read formulas. So these works are more or less simultaneous. And third is this work. So let me give a definition of ROABP. ROABP is product of matrices where the entries are linear polynomials, which are dependent or could be some degree D polynomial, which depend on a particular variable. And you multiply it left and right by two vectors. And this permutations of variable, pi denoted here, is referred to as variable order of the ROABP. So this model has found lots of applications in various fields. So one can look at it that PIT for ROABP is the algebraic analog of RL versus L question. It contains lots of interesting polynomials. It can compute lots of interesting polynomials and contain lots of interesting classes. And also just doing PIT for this has given us applications to non-commutative ABP PIT and special case of Noether normalization lemma. So just to talk in detail about ROABP, three parameters to keep in mind are number of variables, So you're multiplying matrix of size of the matrix, which is denoted by W, and individual degree of the polynomials, which are entries in these matrices. So N, W, and D are to be kept in mind. So there have been works on PIT for ROBP. So roughly the size of the hitting set is of the size NDW to the order log n. And it is still open to get a poly-size hitting set for this class. So a special class of ROBP is commutative ROBP, where there is an assumption that all these matrices commute with each other. So there have been works on this as well by Forbes, Silka, Saptarshi, and Gurjar et al. And roughly here also, the time complexity is again NDW, somewhat quasi-polynomial, but the exponent is slightly less. And again, it's still open to construct poly-size hitting sets for this model as well. We study hitting sets for orbits of ROBP. So the first result on this was by Saha and Thanke, who gave NDW to the order D log W size for commutative ROBP and N omega to the. So again, these specific size doesn't really matter right now, but they gave it for multilinear polynomials for ROBP. So in this work, what we do is we improve both these hitting sets, and in particular remove the multilinearity assumption on the second result. So what our results are? So we give a NDW to the power of minimum of omega square to the 2D log W size hitting sets for commutative ROP, and NDW to the omega square log n times min of omega square 2D log W size hitting sets for orbits of ROP without any individual degree. So one can observe, if you focus on it, then you can observe that in the low width setting, our first result will dominate what was known before and will match if it's not low width setting. And our result for orbits of ROBP is improvement when the individual degree is large. So let me give a quick overview on the template, how we design this hitting set. So if your polynomial belongs to orbit of some other polynomial, then you can think of it f is equal to h of Lx, where Lx is some invertible linear transformation. So your goal is to design hitting sets for this polynomial, assuming it has some h has some nice structure. So previously we used to just shift our polynomial and hope to get some structure to design hitting sets. But in this model, what happens is, if you're looking at orbits, if you shift your polynomial, you lose control over your shift. So you get a transform shift. Since you don't know what the invertible linear transformation is, you don't really have control over the shift. Nevertheless, one can still work with this, and we show exactly this, that if you can somehow ensure that the shift is a conjugation with an invertible linear transformation, then you can still say something. So for instance, if you look at shift orbits of sparse polynomials by choosing some shift smartly, one can ensure that if you apply any invertible linear transformation, all its coordinates will be non-zero. And there is a result by Forbes, that is, if you shift a sparse polynomial, then there is a log s support monomial present there. And using this, one can just observe that even after applying the linear transformation, one can observe that there is a d log s part homogeneous component which is still non-zero. And this directly gives us a hitting set for orbits of sparse polynomials when the individual degree is small. So roughly this is the template of our ideas, and we use this template along with known techniques from Forbes, Silka, Saptarshi, and the Spilka-Volkovich generator to get our results. So to conclude, so we gave better hitting sets for orbits of ROBPs and commutative ROBPs. I would like to end up with an open question. Although we have improved slightly the size of the hitting set, there are still wide gaps between size of the hitting sets of ROBP and size of hitting sets of orbits of ROBP. And the nice question is, can we close this gap somehow? And with that, I would like to conclude my talk. Thank you.
Thank you. If there are any questions, then maybe we can take it up in the discussion. In the discussion time, so that William can set up for the next talk. Okay. Great. So yeah, our next speaker will be William Hosa, who will be talking about better pseudo distributions and de-randomizations for space-bounded computation. Please go ahead.
Okay, thanks. And hopefully, you're all hearing me and seeing my slides. So this work is about pseudo distributions and the de-randomization of space-bounded computation. So recall that BP space S is the class of languages that can be decided by randomized algorithms that use O of S bits of space. And the popular conjecture is that BP space S coincides with deterministic space S. Right, so this conjecture is saying randomness is not actually necessary for space-efficient computation, so you might as well throw all your fair coins into the trash can. To try to prove a conjecture like this, we'd like to understand, what are these algorithms doing with their random bits? And so the first observation is that if you fix the input and then consider the behavior of this algorithm as a function of its random bits, then that function can be computed by a model of computation called a bounded width read-once branching program. And if you haven't studied this model before, that's okay. Just the point is that it captures the action of space-bounded algorithms on their random bits. And so the traditional approach to de-randomizing space-bounded computation is to try to design a sufficiently powerful pseudo-random generator. Right, so a pseudo-random generator, as a reminder, is a function that stretches a short r-bit truly random seed out to a long n-bit pseudo-random string. And what we mean by that is that for every polynomial width read-once branching program, the expectation of the program is essentially the same up to some small error epsilon in two scenarios. Right, the first scenario is that you plug in truly random bits, and the second scenario is that you plug in pseudo-random bits from the generator. Now, if we could design a log space computable pseudorandom generator for this model with the optimal seed length, which would be log n over epsilon, that would immediately imply a full de-randomization of space-bounded computation. Okay, in particular, it would imply that L equals BPL. But so far, we're not there yet. The best pseudorandom generator for this model that's known is a construction by Nissan from 3 decades at this point, and it has seed length log squared n plus log 1 over epsilon times log n. Okay, so it's basically quadratically worse than what we want. There's been a lot of effort trying to improve this seed length, and there's been success in special cases, but for this most fundamental problem, this seems to be a very stubborn problem. It has resisted our attacks. And so that makes us think well, maybe we should, stop trying and maybe try to think outside the box. It's not like there's some law that says if you want to de-randomize algorithms, you have to design a pseudo-random generator, right? Maybe we can de-randomize algorithms without having to design a better pseudo-random generator. And in particular, we can try designing some kind of relaxation of the concept of a pseudo-random generator. And so what I'm talking to you about today is one particular relaxation of the concept of a pseudo-random generator, something called a weighted pseudo-random generator. This is a concept that was introduced a few years ago by Braverman, Cohen, and Garg. So the definition is we have a pair now, G comma rho. So G is still a function that stretches r bits out to n bits. And now rho assigns a real weight to each seed. Okay, so it's a weight function. And the requirement is that for every polynomial width read-once branching program, F, the expectation of the program is essentially the same in two scenarios. Okay, the first scenario is still we plug in truly random bits. The second scenario now is we pick a random seed, stretch out the seed using G and feed that into the program, and then multiply by the weight of that seed. Okay, so the key thing to keep in mind is that this weight function, these weights are allowed to be negative. Okay, and so that opens the door for the possibility that if we orchestrate things just right, maybe we can have some error cancellation. Okay, so that's the sort of motivating idea behind this definition. And one can show that these weighted pseudorandom generators are intermediate between true pseudorandom generators and the traditional concept of a hitting set generator, which is like a one-sided version of a pseudorandom generator. And weighted pseudorandom generators would still be sufficient for de-randomization. If we could design explicit optimal weighted pseudorandom generators, then that would still imply L equals BPL, just as if we had a true pseudorandom generator. When Braverman, Cohen, and Garg introduced this concept of a weighted pseudorandom generator, they gave a construction with seed length O tilde log squared n plus log 1 over epsilon. Okay, so this construction is better than Nissan's generator when epsilon, the error parameter, is very small. Like think of maybe epsilon as like inverse quasi-polynomial. Okay, now admittedly, I mean, the log squared n term is really the term that we would have preferred to improve. It's like the more important term in the seed length here. But because it had been so long with no improvement on this, this fundamental problem, I mean, an improvement in any regime of parameters is exciting and interesting. The other unfortunate thing is that Braverman, Cohen, and Garg's work was pretty complicated. Their construction and analysis were complicated, and so that motivated researchers to try to find like simpler constructions. And at this point, there have been several follow-up papers getting like simpler constructions of more or less the same phenomenon. And one of the benefits of these simpler constructions is that we're able to shave off some of these log-log factors that were present in Braverman, Cohen, and Garg's original work. And so at this point, and this is the main theorem of the paper, at this point, we have explicit weighted pseudorandom generators for polynomial width read-once branching programs with seed length O of log squared n plus log 1 over epsilon. And the proof of this theorem is based on a more general transformation, an error reduction procedure. So it's this generic transformation that takes any moderate error pseudorandom generator and transforms it into a low error weighted pseudorandom generator. Okay, so in both cases, we're fooling polynomial width read-once branching programs, but we start with like inverse polynomial error, which we're thinking of as like moderate error. And then we transform it into something that has low error, epsilon, where epsilon is maybe inverse quasi-polynomial. And of course, we have to pay for that in terms of the seed length, but we only pay a little bit. We go from seed length r to seed length r plus log 1 over epsilon. Okay, and this error reduction procedure is based on some very recent prior work where they developed a similar error reduction procedure. So this was by Cohen, Duran, Renard, Sperlo, and Toshima, and then independently by Pine and Vadan. And our error reduction procedure is extremely similar to theirs. It builds on, it builds very much on their work. It just has, one little twist. And that little twist is that at one point in the construction, we use something called a randomness efficient sampler. And that little twist, lets us get rid of, this last like log factor. I also want to mention another theorem that's in the paper, which is an application, which I think helps to motivate this whole line of work. The application is a better unconditional de-randomization of space-bounded computation. So since the 90s, the best unconditional de-randomization has been this theorem by Sachs and Zhou, which says that BP space S is contained in deterministic space S to the 3/2. Today, we're able to just slightly improve this bound by shaving off a factor of square root log S. Okay, so the new bound is S to the 3/2 over square root log S. So, I mean, this is, just barely any better than the Sachs-Zhou theorem, but I hope that maybe it can kind of like break a psychological barrier because it shows, there's room for improvement. And I don't see any particular reason for this to be the end of the road either. I mean, hopefully we can improve it even further. So the proof of this theorem uses like the Sachs-Zhou framework, their algorithms, and then combines it with some of this recent work on weighted pseudorandom generators. And I want to emphasize that it actually only requires recent prior results on weighted pseudorandom generators. So for this application, it's not actually necessary to use this last incremental improvement in the constructions of weighted pseudorandom generators. Okay, so just to wrap up, let me just make a couple of quick comments about this concept of weighted pseudorandom generators that we're still sort of getting used to and learning about. It seems to be that weighted pseudorandom generators really are easier to construct compared to true pseudorandom generators. This extra flexibility in the definition that, with this weight function really seems to open some new doors. But at the same time, the weighted pseudorandom generators are still useful once we've constructed them, right? This application to de-randomization is really showing, that these things are useful. And in particular, they seem to be more useful than the traditional concept of hitting set generators. And so it seems that weighted pseudorandom generators are sort of this Goldilocks concept that are striking a nice balance between these two competing goals of being easy to construct and useful once you've constructed them. Okay, so that's all I have to say. Thanks for listening.
Thank you. So are there any questions? So, Vilik, what is the best sort of seed length that we currently know for hitting set generators for small width computation?
Yeah, good question. So it's basically the same. So this work basically brings weighted pseudorandom generators in line with the state of the art for hitting set generators.
Okay.
There is one tiny exception. There is one regime where we still have slightly better results for hitting set generators, and that's when we're dealing with like very wide but short read once branching programs, or in other words, we're dealing with like randomized algorithm. If we're trying to de-randomize algorithms that only use a few random bits in the first place, then in that setting, there is still a slight gap where the hitting set generators are, so we have optimal hitting set generators for the case of like algorithms that only use polylogarithmically many random bits. We have optimal hitting set generators for that setting, whereas for like pseudorandom generators or even weighted pseudorandom generators, we still don't have quite the right dependence on the error.
Okay. If there are any further questions, maybe we can take it up in the discussion time afterwards. And Dean, do you want to set up?
Great. Do you guys hear me?
Yes, and we see the slides as well. Okay.
Okay.
So the next talk is going to be by Dean Doron, titled Pseudorandom Generators for Monotone Read Once Branching Programs. Yeah, please go ahead.
Thanks, Mohammad. This is joint work with Raghu Meka, Omer Reingold, Avishai Tal, and Israel Badhan. Good. So William just talked about the BPL versus L problem and the PRG approach to the problem. Namely that to de-randomize BPL, we need to full read once branching programs of width, meaning the number of states at each layer, which is polynomial in the length. Now, one way to make progress on the problem is, like we just heard, is by investigating the low error regime, which is the third line in this table. But another prominent way is to restrict ourselves to constant width. Now, it's not sufficient to randomize BPL, but maybe getting better seed length in the constant width case will give us new insight to the more general problem. So W=2 case is well understood since the 90s. And for W=3, only recently, Meka, Reingold, and Tal had a major progress and got nearly logarithmic seed length in the high error regime. And what about W=4? There, actually, the best we know is Nissan's generator, which gives us log squared n, even for a constant L. So maybe to better understand the constant width case, let's impose even more structure on the branching program. Now we can view each layer of the branching program as given by a function that gets the current state and some edge label. It can be 0, 1, but it can be from a larger alphabet, and outputs the next state, right? Now, if for any fixed edge label, the function from W to W is a permutation, this is a fairly, it's a more understood model, although we have important and interesting open questions there. And for this work, we want to handle the other extreme, where each EI, where we fix the edge label, is a monotone function of the states. Okay, so in other words, a monotone branching program is such that the edges associated with each edge label do not cross. So let's see it in a picture. So here is a monotone layer. So say the black edges are the 0 edges and the gray edges are the 1 edges. And you see that each function on its own is a monotone function. Okay, so what's our result? We get PRGs for monotone ROBPs with nearly logarithmic seed. So for any n, w, and epsilon, we have an explicit PRG that stretches t bits to n bits, fooling with w, length n, monotone ROBPs with r epsilon, and the seed length is O tilde of w squared log n over epsilon. It also works for any order, but I'm not going to get into the any order definition. Okay, good. So a natural question is, what's the strength of such monotone ROBPs? So they extend constant width read1 zeta0 formulas. Namely, a depth W read1 zeta0 formula can be computed by a width W+1 monotone ROBP. So that's good because it's a natural class, and we actually already had PRGs for this class. But also, we proved that they strictly extended. So there are natural functions computable by constant with monotone ROBPs. They're not computable in read1 zeta0. Okay. So what's the high-level approach of our construction? So we followed the successful iterated pseudo-random restrictions approach due to Idai and Vigorson, and further developed by Gopalan, Mekar, Reingold, Terveson, and Budhan. And this approach was actually recently used for constructing many PRGs for arbitrarily ordered BPs, for width-3 BPs, for product tests, for read1 formulas. And there, what we do is we do a series of random restrictions with the hope that finding a smooth version of the restricted function is easier. So we want the restricted function to get simpler. Now, this approach has two main components. The first one is we need to make sure that we preserve the function's expectation on average over the restrictions. And for this, we use an off-the-shelf result by Forbes and Kelly, which gives us exactly that. The second component, which is the bulk of our work, is that we need to make sure we simplify enough within few iterations. Okay, now I want to mention where monotonicity helps here, and it helps a lot. So we said that layer I is colliding if two edges with the same label are mapped to the same vertex. So you see the ith layer here, if we restrict, if a restriction sets xi, it sets it to a fixed value, say it sets it to 0, then we say the collision is realized. And why it is helpful? Because it introduces a layer of width W minus 1. So you see that after the restriction, we will have one vertex which is not reachable. And the nice thing is that in a monotone branching program, every non-identity layer, every meaningful layer, is actually a collision layer. And furthermore, this property is preserved under restrictions and what's called grouping together layers, which is another helpful tool where we treat multiple layers with edge labels in 0, 1 as like a bunch of layers, as a single layer over a much larger alphabet. And this a simple trick allows us to consider the size of the alphabet of a smaller width branching program as our progress measure for simplification. Okay, so for our PRG, what we want is to reduce the width by iteratively applying width reduction. So we start from width W, and sigma, we could start with 0, 1, but we want to kind of iteratively do this. So we start with 0, 1 to the O log n over epsilon. And to reduce the width to W minus 1, we do the following iterative process where we restrict to create a width W minus 1 layers between many width W ones. We further restrict to reduce the alphabet and kind of do this procedure for log n over epsilon iterations. And eventually, what we can show is that we can actually write the width W branching program as a width W minus 1 branching program after all these restrictions over 0, 1 to poly log n over epsilon. And then we want to return to kind of the base alphabet size of 0, 1 to the O log n over epsilon. And you can view this as we reduce the distance between each two W minus 1 layers until we can just treat the branching program as having width W minus 1. Okay, now each this super iteration takes roughly W log n over epsilon random bits. So altogether we get the C lengths that I mentioned. Okay, I know this was all hand wavy, but of course you're welcome to ask me more in the closer session. Okay. Thanks.
Thank you. Are there any questions while Liang sets up? Okay, maybe we'll take the questions in the discussion session later on. Liang, would you want to go ahead and share screen, etc.? You'll have to move left to the podium.
Does this work?
Yeah.
Can you see everyone sees my screen? Oh no.
I don't yet see your screen though.
Okay.
I don't know if it's because I'm...
No, I should have figured this out, but let me try this. Yeah?
it's not yet up for me.
Oh, I'm so sorry about this. It needs permission to access your input so others can see what. Please go to operating systems. Oh, hold on.
Do you use Chrome, Liang?
I do use Chrome, but I'm trying to share a PowerPoint. How do I do this? Screen share. Oh, just a window. Sorry, I think I figured it out. Yeah? No?
We still don't see it.
Sorry about this. It's not allowing me to share my screen. Has anyone encountered this? If not, I can just give it without slides, which would be an experience. Has anyone? No.
Do you want to try it with a different browser, maybe, or something?
No. Well, oh, I see. Well,
You can use Safari, but not Firefox.
I'm using Chrome, but ugh, sorry. Well, maybe I should just give it without slides. It's going to take a while.
Now we can't hear you much either.
Oh, thanks, Mary.
Yeah, your voice is extremely faint for me. I don't know if it's the same for the rest.
Then click on the window. Yeah, I'm just yeah, thanks, Mary, but I'm clicking on PowerPoint and click share, but it's not sharing.
By the way, we can't hear you much, Liang.
No? Can you hear me?
Yes.
Can you hear me now?
Yes, we can.
Okay. Well, I'm not able to share my screen. I'm so sorry, but maybe I'll just give the talk without slides. Should I try that? Okay. Well, sorry about this. Well, thanks for sticking around for the final talk, and I'm sorry about this this tech troubles. Happy to see so many friendly names. Well, since the last talk, I would just like to thank Mary and the session chairs for a great conference. Okay, let's see how this goes. I have my slides in front of me. Well, the title of my talk is Deterministic Approximate Counting of Polynomial Threshold Functions via De-randomized Regularity Lemma. It's a mouthful and especially tough to follow without slides, but let me do what I can. Okay, so this is a talk about deterministic approximate counting. I think we can digest this without a slide. Just to quickly recall the definitions, you pick your favorite circuit class C of Boolean circuits. And what's the goal? The goal is deterministic approximate counting. Well, given a function f that's in this class C, I'd like to design a deterministic algorithm, which you can look at the circuit, you can query it, and your goal is to come up with an accurate estimate, say plus minus epsilon, accurate estimate of, well, you're trying to count. You're trying to count the fraction of satisfying assignments. Okay, so again, you're given as input a function from this circuit class C, And your goal is to come up with an efficient deterministic algorithm that approximates the probability of acceptance up to plus minus epsilon. And the name of the game here is a deterministic algorithm, right? This is trivial with a randomized algorithm. Just do a bunch of random sampling. Okay, so we are interested in deterministic approximate counting. Very basic problem in de-randomization. And why do we want to do this? A very basic motivation for this problem is the P equals BPP problem. If you can do this for all circuit classes C, for the circuit class C being all poly n size circuits, then it's an easy exercise to see that this implies that P is equal to BPP. It's almost the very definition of what it means for P is equal to BPP. And this will be fantastic, but it's unfortunately too much to hope for given the current state of the art. We are unable to do deterministic approximate counting for the class of all poly-size circuits, just like how we're unable to prove lower bounds against the class of all poly-size circuits. So what do? We do what we do in circuit complexity, which is to scale down our ambitions for now. We study deterministic approximate counting for various restricted classes of circuits. Okay, so I have here on my slides, which you cannot see, various classes of circuits that people have studied a lot. Well, rather than poly-size circuits, consider just poly-size DNF formulas. Can you do deterministic approximate counting for poly-size formulas? CNF formulas. If so, how about AC0 circuits, right? So that's one flavor. Of course, branching programs, extremely well studied. Intersection of half spaces, a more geometric object, but it's very natural. You're given some sort of polytope living in n-dimensional space. Please count for me the fraction of inputs that fall within your polytope. And in this talk, we are focused on sort of the more geometric side of things, a polynomial threshold function, which I'll define next. It's a generalization of a linear threshold function, which is a half space. So this is like the sign of a low degree polynomial. Okay, and we're interested, given query access, or maybe given an explicit representation of the sign of a low degree polynomial, please deterministically output its fraction of satisfying assignments up to plus minus 0.1. Okay, great. Any questions? Okay, my voice still coming through? Okay, great. So that's the problem we're interested in. And as we all know, there's a very natural connection to pseudo-random generators. In fact, so let me quickly outline that connection. So a natural approach to deterministic approximate counting for any class C, doesn't have to be polynomial threshold functions, is to construct a pseudo-random generator. And by now, this is like the fifth talk of this session on de-randomization. We all know what a PRG is, but briefly, it sort of like stretches a uniform R-bit seed into n bits, where we think of R as much smaller than n, such that it fools every circuit in your circuit class C. And in this talk, think of the circuit as a polynomial threshold function, the sign of a low degree polynomial. So again, for every function f in the class C, its true acceptance probability, if you fed it a truly random n-bit string, it's up to plus minus epsilon close to f on your pseudo-random string that's output by your pseudo-random generator. Okay, so that's what a PRG is. And why is it that the PRG gives a counter? Well, that's probably like the very motivation for the definition of PRG in the first place. A PRG clearly, easily gives a deterministic approximate counter. What do? You just enumerate over all 2 to the r seeds, whereas r is your seed length. Okay, so here on my slide, I have that PRGs is a powerful object that solves this algorithmic problem we're interested in of deterministic approximate counting. But in fact, sort of like maybe in the same spirit as William's talk, it solves a harder problem. And if all you care about is deterministic approximate counting, you do not have to construct a PRG, right? It gives you a PRG gives you a counter, but if you do not have to design a PRG in order to get a counter. So in what ways are PRGs more powerful? Well, they're sort of, crucially, they're input oblivious, right? You have a single PRG that works for all functions in your circuit class. So it doesn't look at the circuit, it only makes use of queries to the circuit as a black box. So that's, on one hand, the power of a PRG. But on the other hand, if all you care about is approximate counting, maybe you can try to use the fact that you can look at the circuit, right? So that's one sort of strength of a PRG that's beyond what we need for approximate counting. And the other is that PRGs can find satisfying assignments, whereas a PRG spits out a set of seeds, a set of inputs, and it approximates the true acceptance probability. So within that batch, a good fraction will be satisfying if your original circuit had a good amount of satisfying assignments. Whereas a counter, it just spits out like a number. It doesn't give you a satisfying assignment. So the point of this slide is to say that counting is, in some sense, could be an easier problem than designing a PRG. Okay, so a natural question is, can we be more efficient if we only want a counter rather than a PRG? Right? PRG is great. There are other applications, but if all you care about is counting, can you get a better counter than a PRG? And such a phenomena has been observed before. For the case of DNFs, depth 2 circuits, the best known PRG has seed length log squared n, roughly. So that gives immediately implies approximate counting in time n to the log n, which is great, but it's not poly n. And there's this very nice work of Gopalan, Mecca, and Reingold gives a non-PRG based deterministic approximate counting in time n to the log n. So PRG gives you n to the log n, whereas if all you care about is counting, you can do it n to the log n time. So that's a big qualitative difference. And the main result in this work is to give the same difference, gave the same phenomena for polynomial threshold functions. So now we can count polynomial threshold functions faster than what's given by a PRG for polynomial threshold functions, which is designing a PRG is, quite challenging. Okay, and it's a very well-studied problem, work of Zuckerman, Mecca and Zuckerman started it off. There's a lot of work on it, but it's still not very well understood. And now, given our work, we can do slightly better for counting than for PRGs. Okay, so I have a slide here on the definition of a polynomial threshold function. I'm not sure if I'm running out of time, but it's the sign of a low degree polynomial. So sort of it's parameterized by d, which is the degree. So, and your running times, you want as good a dependence on d as possible. And our main result, so how do we achieve this? The fact that we can count faster than we can fool. We give a method, and this explains part of the title, that just allows us to solve the problem over Gaussian space rather than Boolean space. And Gaussian space is a special case. It's an easier setting than a Boolean setting. This is not too hard to see. It's basically if you sum like a bajillion random bits, it's going to look like a Gaussian. So the Gaussian space is a special of the Boolean setting, and we allow. So the main contribution of our work is a method that allows us to reduce the problem of counting over Boolean space into that of counting over Gaussian space, which is quite a bit easier. And there are techniques that can exploit the specific structure of Gaussian space to get faster Gaussian running times. And sort of the main new structural result is a
Yeah.
Sorry. All right, great.
Sorry.
All right, thanks. Sorry again about that.
Maybe you can just summarize and
Well, that's it. Well, we can get Gaussian running times for Boolean space, and the main result is the way we achieve it is a regularity lemma, which decomposes every sort of Boolean PTF into a bunch of Gaussian PTFs. All right, thanks.
Further questions, maybe we can take it during the discussion time. Mary, would you like to say something?
Yeah, am I presenting now? Well, yeah, since this is the end of the conference, I just wanted to take this opportunity to thank all of the authors and the whole PC for all of their work sort of putting together this great conference. So thanks so much, everybody. And of course, now the conference is not quite over because we do have discussion time now. So I guess I'll see y'all out in the lobby.
The speakers, and we'll meet outside in the lobby.